Welcome to Learning with UNP. In this session of Data Science and Mastering Machine Learning, we are going to understand about support vector machine practical implementation on a project. In here, we are going to use SVM to solve a classification problem. The objective of this project is to build a predictive model using the support vector machine algorithm to classify whether a person has diabetes or not. By analyzing specific features from a dataset, we aim to determine the likelihood of a diabetes diagnosis. Let me give you an overview of what exactly we will be doing in this project. In this project, we will implement the machine learning process using Python. We will load and explore a diabetes dataset, split it into training and test sets, build and train a SVM classifier, and evaluate the model's performance with appropriate metrics. We will use pandas, numpy, scikit-learn, and matplotlib for this task. Let's begin with understanding the dataset. The dataset name is Diabetes Dataset. This dataset is originally from the National Institute of Diabetes and Digestive and Kidney Diseases. The objective of this dataset is to diagnostically predict whether a patient has diabetes based on certain diagnostic measurements included in the dataset. This dataset was carefully selected with specific criteria to ensure consistency and relevance in the analysis. All instances were selected from a larger database with the following constraints. Each patient is a female of Pima Indian heritage and at least 21 years old. This focused selection helps in maintaining a homogeneous sample, ensuring that the findings and predictions are particularly applicable to this specific demographic group. The constraints help in minimizing variations that could arise from different ethnic backgrounds or age groups, thereby providing more reliable and targeted insights into diabetes prediction for this population. This dataset includes independent variables like pregnancies, glucose, blood pressure, skin thickness, insulin, BMI, diabetes pedigree function, and age. The target variable is outcome, which we will express as 1 for yes, the person has diabetes, and 0 for no, the person does not have diabetes. To begin our project, the first step is to load the diabetes dataset into our Python environment. We will use the pandas library, which is widely used for data manipulation and analysis in Python. Below are the elaborated steps and code to load the dataset. First, we'll import pandas and numpy. Then, we'll load the dataset from an Excel SX file into a pandas data frame. Finally, we will inspect first few rows to understand the data structure and content. Here is how we import various libraries. NumPy as NP for numerical operations, Pandas as PD for data manipulation and analysis, Seaborn as SNS for statistical data visualization, Matplotlib to display plots inline in Jupyter notebooks. Now we will load the diabetes dataset into a Pandas data frame using the read underscore Excel function specifying the path. This allows us to easily manipulate and analyze the data. In here, data.shape gives the number of rows and columns in the dataset data. This output indicates that our dataset comprises 668 rows, which are instances, and 9 columns, which are attributes. These attributes include features such as glucose levels, blood pressure, BMI, and age, along with a target variable indicating diabetes presence or absence. Understanding the shape provides a quick overview of the dataset size and structure, crucial for data exploration and modeling. Before using the SVM algorithm, you may need to preprocess your data if required. This can include cleaning the data, handling missing values, and encoding categorical variables. This line of code checks for missing values in each column of the data frame data and sums them up. In this dataset, there are no missing values in any of the columns, as indicated by the output of zeros for each attribute. After carefully checking, we found no missing values in our dataset, meaning all entries have all the necessary information. Also, all the data is in numbers already, so we don't need to change anything about how it is stored. This allows us to proceed directly with applying the SVM algorithm without needing to handle any missing data, thereby simplifying our pre-processing steps. Now, let's move on to the next step of separating features. To prepare our data for the SVM classification model, we need to separate the features from the target variable. In our diabetes dataset, the features are the medical predictors, while the target variable is the outcome, which indicates whether a person has diabetes or not. We create two variables, X contains all feature columns obtained by excluding the outcome column from the dataset, while Y contains only the outcome column, which serves as our target variable. This separation is essential for training the SVM model as it allows us to provide the algorithm with the input data X and the corresponding output labels Y separately. This way, the model learns to predict diabetes based on the given medical predictors. Now, let's look at train test split method. To effectively evaluate the performance of our SVM classification model, we split our dataset into training and testing sets using the train test split function from the scikit-learn model underscore selection module. This function partitions our data into four distinct arrays: xtrain, xtest, ytrain, and ytest. Xtrain and ytrain are used for training, containing a subset of features x and corresponding target values y. X-test and Y-test are kept aside for testing, ensuring the model's performance on unseen data. The test size parameter set to 0.3 determines the test size, that is 30%, with the remaining data allocated for training. Random set ensures reproducible result across runs. This split allows us to train the model on one portion and validate its performance on another, ensuring reliability and effectiveness. The code is shown here. Over here, let's look at model building. In the context of support vector machines (SVM), there are two primary types: support vector regressor (SVR) and support vector classifier (SVC). The choice between them depends on the nature of the dataset and the goal of the analysis. In our case, since we are working with a classification dataset where the objective is to predict discrete classes, specifically whether a person has diabetes or not, we will utilize the support vector classifier SVC. We start by importing necessary libraries from sklearn.svm, including the SVC module, which enables us to implement the support vector classifier SVC for classification tasks. This import provides functionalities for constructing the SVC model, fitting it to our training data, predicting outcomes, and evaluating model performance metrics, ensuring we have all tools needed for efficient model building and analysis. Here is the code of it. Next, we initialize the SVC model with a linear kernel using SVC kernel is equal to linear function. This setup configures the support vector classifier to fit a linear relationship between the input features and the target variable. The code is shown here. In support vector machines SVM, different types of kernels can be used to transform the input data into the required form. These kernel types include linear polynomial, poly, radial basis function RBF, and sigmoid. Each kernel type serves a specific purpose and helps in capturing various patterns and relationships in the data depending on the complexity and nature of the dataset. Once initialized, the SVC model is trained using the training data, xtrain and ytrain. This process involves the model learning from the data to grasp the relationship between features and their corresponding target outcomes. During training, the model adjusts its internal parameters based on patterns identified in the training set, aiming to optimize prediction accuracy for new or unseen data points. This step is crucial for preparing the model to make accurate predictions based on learned patterns from the training data. The code is shown here. After fitting the model, it can make predictions on new data points. Using the testing data xtest, the predict method applies the trained SVC model to estimate the target variable ypred. These predictions represent the model's best estimates for each input in the testing dataset. Here is the code of it. This data frame compares the predicted values ypred with the actual values ytest from the testing dataset. By visually inspecting this comparison, we can evaluate how closely the SVC model's predictions align with the actual outcomes. This assessment provides insights into the model's accuracy and highlights areas where further refinement may be needed. It's crucial for comprehensively evaluating the model's performance and making informed decisions about deploying it in practical scenarios. Finally, let's move on to understanding the evaluation metrics. To evaluate the model's performance, use metrics such as accuracy, confusion matrix. These metrics will help you understand how well the model is predicting the target values. First comes accuracy score. The accuracy score function from sklearn metrics calculates the accuracy of our SVM classifier model by comparing predicted values ypred with actual values ytest. It quantifies the proportion of correct predictions relative to the total number of predictions on the tested dataset. This metric offers a clear assessment of the model's overall performance in accurately classifying instances into their respective classes. Here is the code of it, which yields accuracy as approximately 79%. The confusion matrix function from sklearn matrix generates a matrix based on predicted values by pred and actual values by test. This matrix provides a visual representation of a classification model's performance showing counts of true positives, true negatives, false positives, and false negatives. Each cell in the matrix reveals how accurately the model classified instances, offering insights into its ability to distinguish between different classes. Here is the code of it, which yields an array representing confusion matrix. Let me explain you each value clearly. True negatives. 120 instances were correctly predicted where the actual outcome was no diabetes. False positives. 10 instances were incorrectly predicted as diabetes when the actual outcome was no diabetes. False negatives. 32 instances were incorrectly predicted as no diabetes when the actual outcome was diabetes. True positives. 39 instances were correctly predicted where the actual outcome was diabetes. This matrix provides a detailed breakdown of how well the model performed in classifying instances into the respective classes, highlighting its strengths and areas for improvement in distinguishing between different outcomes. Furthermore, to enhance interpretability, the SNS.heatmap function from the Seaborn library is used to create a heatmap visualization of the confusion matrix CM. This heatmap displays the matrix with annotations to show the numerical values in each cell. Here is the code of it. This visualization provides a clear representation of how well the model classified instances into their actual and predicted classes, highlighting areas of correct and incorrect predictions. Lastly, the classification report function from sklearn metrics generates a comprehensive report summarizing key classification metrics: precision, recall, F1 score, and support, the number of occurrences of each class in y-test. Precision measures the accuracy of positive predictions. Recall measures the proportion of actual positives that were correctly identified. And the F1 score provides a harmonic mean of precision and recall. This report offers a detailed breakdown of the model's performance across different classes, helping to gauge its effectiveness in correctly identifying instances of diabetes and non-diabetes based on the dataset. Let's break down this evaluation metrics and understand it in a better way. Precision. Precision for no diabetes class 0 79%. Out of all instances predicted as no diabetes, 79% were correct. Precision for diabetes class 1 80%. Out of all instances predicted as diabetes, 80% were correct. Recall. Recall for no diabetes class 0 92%. Out of all actual instances of no diabetes, the model identified 92% correctly. Recall for diabetes class 1 55%. Out of all actual instances of diabetes, the model identified 55% correctly. F1 score. F1 score for no diabetes class 0. 85%. A balanced metric combining precision and recall for no diabetes. F1 score for diabetes class 1 65%. A balanced metric combining precision and recall for diabetes. Accuracy. Overall accuracy of the model 79%. The percentage of correctly predicted cases out of the total. Macro average. The average of precision, recall, and F1 score for both classes, treating each class equally. Weighted average. The weighted average of precision, recall, and F1 score considering the number of instances for each class. These metrics provide a comprehensive evaluation of the model's performance in classifying instances into no diabetes and diabetes categories, highlighting its strengths that may require improvement. This is all about today's lecture. See you in the next lecture. Thank you.